If you take a fluid droplet and let it fall on a fluid bath, the drop simply merges with the bath. But now what if we rapidly oscillate the bath? Using a high-speed camera, we see that the droplet now bounces indefinitely on the bath surface. Remarkably, if we shake the bath harder, the droplet starts to walk horizontally, propelled by the waves generated at its previous impacts. To better visualize the drop's horizontal motion, we capture only one image per bounce, as indicated by these red dots. This results in a strobed video that shows the walking droplet surfing along a guiding wave field, called its pilot wave. To study this pilot wave system, we mathematically model a drop's horizontal motion using a differential equation. Each term accounts for a factor influencing the drop's motion. The first term accounts for the drop's inertia, while the second term accounts for drag forces acting to slow it down. The third term accounts for the propulsive wave force, which is proportional to the slope of the wave beneath the drop. Note that at any instant, the pilot wave is the sum of the waves generated at each of the drop's previous impacts, with the memory time, Tm, governing how quickly each of these waves decay. The longer the memory time, the more the motion of the drop is influenced by its past. Systems like this are called hereditary, as one requires knowledge of both the past and present in order to predict its future evolution. When the memory time of the system is large, quantum-like phenomena are observed. This hydrodynamic pilot wave system is remarkably similar to the pilot wave theory for quantum particles proposed by Louis de Broglie. By drawing mathematical connections between the fluid and quantum models, we can hope to gain insight into the motion of microscopic particles 1,000,000 times smaller than our fluid droplets. Our most recent NSF-funded research has focused on the dynamics of droplet rings, with hopes of gaining insights into the vibrations observed in crystal lattices. Specifically, we are investigating how these rings destabilize as the bath is vibrated more vigorously. For instance, a ring of 3 drops destabilizes into radial oscillations, 10 drops exhibit angular oscillations corresponding to the counter-rotation of 2 pentagonal sublattices, and 20 drops display a remarkable geometrical transition from a circle to a square. Larger rings can be constructed by confining the droplets to a circular channel, and we observe a localized traveling wave called a soliton. Similar solitary waves are observed in the total lattice. Reformulating our pilot wave model in a comparable form allows us to form a mathematical link between these two apparently disparate systems. Based on this link, our experiments provide a means of visualizing the complex dynamics in atomic lattices. Thank you for listening.